Hello friends, I welcome you on my channel Engineering Mathematics DJ Ganit. In this lecture we are going to discuss about eigenvalues and eigenvectors of invertible matrix. We will discuss that if we know eigenvalues of given matrix A, then how to find out eigenvalues of inverse of given matrix capital A. Before that we make some remark. First remark is, this remark says that if our matrix is invertible, then lambda equal to 0 cannot be its eigenvalue. Lambda equal to 0 cannot be an eigenvalue of an invertible matrix, because if lambda equal to 0 is an eigenvalue of a matrix, then matrix is not invertible. And it is true on both sides. If matrix is not invertible, then lambda equal to 0 is an eigenvalue of that matrix. So we remember this remark that lambda equal to 0 cannot be an eigenvalue of an invertible matrix. So if matrix is invertible, lambda equal to 0 cannot be an eigenvalue, and if lambda equal to 0 is not an eigenvalue of a matrix A, then matrix is invertible. In other words, matrix is not invertible if and only if lambda equal to 0 is an eigenvalue of A. So if we know the eigenvalue of an invertible matrix, suppose lambda is an eigenvalue of an invertible matrix capital A, then eigenvalue of inverse of this matrix A inverse is nothing but 1 over lambda, because if matrix is invertible, then lambda is never 0, so we can define 1 upon lambda. So here matrix is invertible, therefore lambda equal to 0 is not an eigenvalue, therefore 1 upon lambda is defined. So if we have eigenvalue of an invertible matrix, say lambda, then eigenvalue of inverse of A is 1 upon lambda, and there is no change in the corresponding eigenvectors. If x is a eigenvector of matrix A corresponding to eigenvalue lambda, then x is the eigenvector of matrix A inverse corresponding to eigenvalue 1 upon lambda. So using this remark, if we want to find out eigenvalues and eigenvectors of inverse of a square matrix, then we don't have to find out inverse of the matrix. We will just find out eigenvalues of matrix A, and then eigenvalue of inverse of A is given by 1 upon lambda, and eigenvectors of A and A inverse remains same, corresponding to lambda and 1 upon lambda. So we find out eigenvalues and eigenvectors of inverse of this given matrix capital A. So again I mention, to find out eigenvalues and eigenvectors of inverse of this matrix, we don't have to find out inverse of this matrix. We will just find out eigenvalues of this matrix lambda, and eigenvalues of A inverse will be 1 over lambda, and eigenvectors will remain same. So first we find out eigenvalues and eigenvectors for given matrix capital A. So first we write down the characteristic equation of this matrix capital A, that is determinant of A minus lambda I equal to 0, and we know that determinant is written by subtracting lambda from the diagonal and keeping other entries as it is. So diagonal will be minus 2 minus lambda, 3 minus lambda, 5 minus lambda, and remaining entries as it is. Now we find out value of this determinant. So we start with the first row. So minus 2 minus lambda into determinant of this 2 by 2 square matrix, which is 3 minus lambda times 5 minus lambda minus 4, then minus 2 times minus 2 into 5 minus lambda minus 2 into minus 4, which is plus 8, and then plus 3 into determinant of this 2 by 2 square matrix, which is minus 4 and minus minus plus 4 into 3 minus lambda equal to 0. Now we take multiplication of these two, which is this part, 15 minus 3 lambda minus 5 lambda plus lambda square minus 4 minus 2 times this we can rewrite as minus 10 plus 2 lambda plus 8 plus 3 times we multiply 4 with this bracket. We further simplify, we can rewrite this as lambda square minus 8 lambda plus 11. We keep this as it is, and this is going to be 2 lambda minus 2. Minus 10 plus 8 is minus 2 and plus 2 lambda, and this is 8 minus 4 lambda equal to 0. And if we multiply all these brackets and if we simplify, we will have this polynomial equation of degree 3. I have to rewrite again, plus 11 lambda minus 6 equal to 0. So as we discussed in the previous lecture, that if we have a polynomial equation with integer coefficients, then integer solution of this polynomial equation is nothing but divisor of constant term, which is minus 6 here. So as we know, divisors of minus 6 are plus or minus 1, plus or minus 2, plus or minus 3 and plus or minus 6. So if there is any integer solution of this polynomial equation, then it must be a divisor of constant term minus 6. So we can try by taking 1 by 1 values. If we put lambda equal to 1, we have 1 minus 6 plus 11 minus 6. So this is 12 minus 12, 0. That means lambda equal to 1 satisfies this equation. So therefore, one factor of this left hand side is lambda minus 1. To find out second factor, we use the method of synthetic division. We write down coefficients of lambda cube, lambda square, lambda and constant term here. So here 1 minus 6, 11 minus 6. And then we put 0 here. We add these two, that is 1. We multiply this each entry with 1 and write here. Again we take addition. Minus 6 plus 1, which is minus 5, minus 5 into 1, that is minus 5, and addition of 11 and minus 5 is 6, 6 into 1 is 6, so we obtain 0 here, and this will give us lambda square minus 5 lambda plus 6 equal to 0. So from this we have lambda minus 1 is 0 and lambda square minus 5 lambda plus 6 equal to 0. So if you factorize this, you will obtain, this is nothing but product of two linear factors, lambda minus 3 into lambda minus 2. So we obtain lambda equal to 2 and 3. So therefore lambda equal to 1, 2, 3 are eigenvalues of A. So from this we can say that eigenvalues of A are non-zero, therefore A inverse exists. So from eigenvalues also we can decide the invertibility of a matrix using that remark. That remark says that lambda equal to 0 cannot be an eigenvalue of an invertible matrix. So here eigenvalues of matrix are non-zero, therefore matrix is invertible. Now we find out eigenvectors corresponding to each eigenvalue, and then we will find out eigenvalues and eigenvectors of A inverse. So now we take, because our matrix is square matrix of order 3, we consider X equal to column vector with 3 components x1, x2, x3. So suppose this X is an eigenvector of matrix A corresponding to eigenvalue lambda. then this x is a non-trivial solution of this system a minus lambda I x equal to 0. So we put value of a minus lambda, and if we simplify, we obtain this system 1. Okay, we have multiplied this matrix with this column matrix, first row into first column, which gives us minus 2 minus lambda into x1, 2 into x2 plus 3 into x3 equal to 0. Similarly, second row into first column, which is minus 2 times x1 plus 3 minus lambda into x2 plus 2 into x3 equal to 0. And last equation is minus 4x1 plus 2x2 plus 5 minus lambda into x3 equal to 0. So first we solve this system for lambda equal to 1. So if we put lambda equal to 1, the first equation becomes minus 2 minus 1, which is minus 3 x1 plus 2x2 plus 3x3 equal to 0. Second equation is minus 2x1 3 minus 1, which is 2x2 plus 2x3 equal to 0. And last equation is minus 4x1 plus 2x2 plus 4x3 equal to 0. So we obtain system of 3 linear equations in 3 unknowns x1, x2, x3. Now we can see here we cannot solve this system directly. It is not easy to solve this system directly, so we apply Gauss elimination. Before that, we can rewrite this system in this way. We multiply all the equations by minus 1. Now we solve this by Gauss elimination. So we start by writing augmented matrix. So as we know, these columns 1, 2 and 3 corresponds to coefficients of x1, x2 and x3. And last column corresponds to right hand side constants, which are all 0. So first column is 3, 1, 2. Second is minus 2, minus 1, minus 1. Third column is minus 3, minus 1, minus 2 and 0. Now to convert this in row echelon form, we require these two entries 0. But if we wish, we can interchange first and second row so that we don't have fractions in further calculations. So we interchange first and second row. Now using first row, we make these two 0. So to make this 0, we multiply first row by minus 3 and add in second row. And for making this entry 0, we operate multiplying first row by minus 2 and adding in third row. So here we multiply by minus 3. So you can see minus 3 plus 3 is 0. Then minus 1 into minus 3, which is 3, minus 2, which is 1. Minus 1 into minus 3, which is 3, minus 3. So we obtain 0 here. And these two entries are 0. So we have 0 here. Similarly, we multiply first row by minus 2 and add in third row. So 1 into minus 2, which is minus 2, and plus 2, it is 0. Then minus 1 into minus 2, which is 2, minus 1. So we obtain 1 here. Minus 1 into minus 2, which is 2, minus 2, 0. So entries below the first non-zero entry of first row becomes 0. Now we concentrate on the first non-zero entry of second row, which is 1 here. So we require this entry to be 0. For that, we multiply second row by minus 1 and add in third row. So there is only one entry which is non-zero here in both the rows. So if we multiply this by minus 1 and add here, we obtain 0 row here. So this matrix is in row echelon form. And all these matrices are equivalent. So these are the first non-zero entries of first and second row. And this first column corresponds to coefficients of x2, second for x2, and this is for x3. So we can see this first non-zero entry of first row corresponds to x1. That means x1 is leading variable. Similarly, this first non-zero entry of second row corresponds to x2. So x2 is also leading variable and x3 becomes free variable because there is no non-zero entry here. So here x1 and x2 are leading variables and x3 is free variable. So the system corresponding to this matrix has infinite number of solutions. So we write down the system corresponding to row echelon form, which is first equation is x1 minus x2 minus x3 equal to 0. Second equation is x2 equal to 0. That means x2 becomes fixed, and if we put value of x2 here, we obtain x1 minus x3 equal to 0. Now x3 is free variable and x1 is leading variable, so we express x1 in terms of x3. So x3 is free variable, that means we can have any value for x3. So therefore in this eigenvector we put x2 equal to 0, x1 equal to x3. Here it is a mistake, x1 is nothing but x3, so this is plus sign. So x1 is x3, x2 is 0 and x3 remains as it is. So we can write this as x3 times 1 0 1. So these are the eigenvectors of capital A corresponding to eigenvalue lambda equal to 1. Similarly, we find out eigenvectors corresponding to eigenvalue lambda equal to 2. For that we put lambda equal to 2 here. So for lambda equal to 2 we have minus 2 which is minus 4x1 plus 2x2 plus 3x3 equal to 0. For lambda equal to 2 this becomes 1. So second equation is minus 2x1 plus x2 plus 2x3 equal to 0. And third equation is minus 4x1 plus 2x2 plus 4x3 equal to 0. So we solve that system corresponding to lambda equal to 2. Okay, this we obtain by putting lambda equal to 2 in system number 1. Now if you observe, first and third equations are same. So we have, if we multiply these two by negative sign, we obtain these two equations, and we again apply Gauss elimination to solve this system. So we write down augmented matrix corresponding to this system, which is 4 minus 2 minus 3 0. Second row is 2 minus 1 minus 2 0. Now to make this entry 0, we have to multiply first row by minus 1 by 2 and add in second row. So we obtain 4 into minus 1 by 2, which is minus 2 plus 2 0, minus 2 into minus 1 by 2, which is 1 minus 1 0, minus 3 into minus 1 by 2, which is 3 by 2 minus 2. So it is 3 minus 4 by 2, we obtain minus 1 by 2, and 0 into minus 1 by 2 0 plus 0. So this is in row echelon form, and we can see this entry corresponds to variable x1 and this corresponds to x3. So therefore x2 is free variable and x1 and x3 are leading variable. So we write down the system corresponding to this row echelon form, which is 4x1 minus 2x2 minus 3x3 equal to 0. And second equation corresponds to second row, which is 0x1 plus 0x2 minus x3 by 2 equal to 0. So from this equation we obtain x3 equal to 0, and if we put x3 equal to 0 here, we have 4x1 minus 2x2 equal to 0, and this we can rewrite as 2x1 minus x2 equal to 0. Therefore we obtain 2x1 equal to x2, and here I made a mistake here. Here x1 and x3 are leading variables and x2 is free variable. So because x2 is free variable, we have to express x1 in terms of x2. Therefore x1 is x2 by 2 and x3 is leading variable, which is 0. So therefore eigenvectors can be written in this way: x1 is x2 by 2, x2 is free variable, so we keep x2 as it is, and x3 has value 0. And if we take x2 outside this matrix, we can rewrite this as x2 times 1 by 2 1 0, and x2 can take any value. So these are the eigenvectors of given matrix corresponding to eigenvalue lambda equal to 2. Now we find out eigenvectors corresponding to eigenvalue lambda equal to 3. So we put lambda equal to 3 here. So for lambda equal to 3, this is minus 5x1 plus 2x2 plus 3x3 equal to 0. This is minus 2x1 plus 0x2 plus 2x3 equal to 0. And last equation is minus 4x1 plus 2x2 plus 2x3 equal to 0. So we solve that system corresponding to lambda equal to 3, and we can see this is also not easy to solve directly. So for this system also we have to apply Gauss elimination method. So we write down the augmented matrix corresponding to this system. First column corresponds to coefficients of x1, which are minus 5, minus 2, minus 4. Second column 2, 0, 2. Third column 3, 2, 2. And last column is 0, 0, 0. Now this is first non-zero entry of first row. So we have to make these two entries 0. So first we take reciprocal of minus 5, which is minus 1 by 5, and negative of minus 2, which is 2. So we multiply first row by minus 2 by 5 and add in second row. Similarly we multiply first row by minus 4 by 5 and add in third row. So that we have written here. So first row as it is, and here we multiply by minus 2 by 5, so we have 2 minus 2, which is 0. Then 2 is multiplied with minus 2 by 5, which is minus 4 by 5 plus 0. Similarly 3 into minus 2 by 5, which is minus 6 by 5. 3 is multiplied with minus 2 by 5 and added in 2. So this is 10 minus 6, which is 4 by 5. And these two are 0, therefore we have 0 here. Then we operate this, multiplying first row by minus 4 by 5 and adding in third row. So if I multiply this by minus 4 by 5, I will have 4, and 4 minus 4 is 0. Then 2 into minus 4 by 5, which is minus 8 by 5. 2 is multiplied with minus 4 by 5, which is minus 8 by 5 plus 2. That is 10 minus 8, which is 2 by 5. Just a minute. Then 3 into minus 4 by 5, which is minus 12 by 5 plus 2. Okay, we multiply this 3 by minus 4 by 5 and add in 2. So we have 10 minus 12, which is minus 2 by 5. And these two entries are 0, so we have 0 here. So now we concentrate on the first non-zero entry of second row. So using this we have to make this 0. So for that we take reciprocal of this, which is minus 5 by 4, and we multiply with negative of 2 by 5, which is minus 2 by 5. So that means we have to multiply with 1 by 2. So we multiply minus 4 by 5, or we multiply second row by 1 by 2 and add in third row. So if we multiply this by 1 by 2, we have minus 2 by 5 and plus 2 by 5, which is 0. And if we multiply this by 1 by 2, we have 2 by 5 and here we have minus 2 by 5, so we obtain 0 here. So now these are the first non-zero entries of first and second row. They correspond to x1 and x2. Therefore x1 and x2 are leading variables and x3 becomes free variable. Now we write down the system corresponding to this row echelon form, which is minus 5x1 plus 2x2 plus 2x3 minus 5x1 plus 2x2 plus 3x3 equal to 0, and second equation is minus 4 by 5 x2 plus 4 by 5 x3 equal to 0. So from second equation we can take this minus 4 by 5 common. So this we can write as x2 minus x3 equal to 0. Therefore x2 is x3. Because x3 is free variable, we can represent x2 in terms of x3. And if we put x2 equal to x3 in first equation, we have minus 5x1 plus 2x3 plus 3x3 equal to 0. So this is minus 5x1 plus 5x3 equal to 0. Therefore 5x1 is 5x3 and therefore x1 equal to x3. So x1 is x3 and x2 is also x3. So now the eigenvector becomes, we put x1 equal to x3, x2 equal to x3 and we keep x3 as it is. And this we can rewrite as x3 times 1, 1, 1. So these are the eigenvectors of matrix A corresponding to eigenvalue lambda equal to 3. So now we are having eigenvectors of given matrix corresponding to eigenvalues of given matrix. So we have find out that lambda equal to 1 is an eigenvalue of given matrix and this is the eigenvector, or these are the eigenvectors corresponding to lambda equal to 1. So as we know, A is invertible and therefore lambda equal to 1 by 1, which is 1, is an eigenvalue of A inverse and eigenvectors remains as it is. So eigenvectors corresponding to lambda equal to 1 is also x3 times 1, 0, 1. Also lambda equal to 2 is an eigenvalue of A and this is the corresponding eigenvector. Therefore lambda equal to 1 by 2 is an eigenvalue of A inverse and eigenvectors remains same. X equal to x2 times 1 by 2, 1, 0 is an eigenvector of A inverse corresponding to lambda equal to 1 by 2. Similarly lambda equal to 3 is an eigenvalue of A. Therefore lambda equal to 1 by 3 is an eigenvalue of A inverse and these two remain same. Here x is x3 times 1, 1, 1 are eigenvectors of A corresponding to lambda equal to 3. Therefore they are the eigenvectors of A inverse also corresponding to lambda equal to 1 by 3. So in this way we can find out eigenvalues and eigenvectors of inverse of a square matrix A if matrix is invertible. So as what we have discussed in today's lecture is, if lambda is an eigenvalue of matrix A which is invertible, then 1 upon lambda is an eigenvalue of inverse of A, and eigenvectors of capital A corresponding to lambda and eigenvectors of A inverse corresponding to 1 upon lambda are exactly same. So this is all about today's session. I hope you like this lecture. Thank you very much.